This conference has around 16 countries involved from the affiliated, and also we have a diversity of 15% of females. In the beginning, we will have some videos, safety videos, as I already advertised. Take care of your notebooks, keep an eye on them, even during the coffee breaks, okay? So, and also another point is that badges are obligatory to enter the dome. You have to always present your badges for security reasons. We are in a big city, so in the middle of the city, and anyone, if eventually enters here, it's hard to control everything, so the form that we found appropriate is to control. If you don't have a badge, it will be hard to enter. You have to call me or call someone to enter. It will be hard to enter here. So let's go further. We have some videos to present. I think just now. Can you start the videos, please?
Bem-vindos ao Instituto Principia. Antes de iniciarmos, pedimos atenção a alguns avisos importantes. Este espaço conta com um sistema de segurança equipado com detectores de fumaça, além de extintores de incêndio estrategicamente localizados próximos às saídas de emergência. Em caso de falta de energia, luzes auxiliares serão acionadas automaticamente. O domo possui 4 saídas de emergência. 2 na parte inferior com acesso ao hall de entrada e 2 na parte superior acessíveis pelas escadas. A entrada e saída usuais devem ser feitas pelo hall. As portas superiores devem ser utilizadas apenas em situações de urgência. Para garantir a segurança de todos, é fundamental que portas e escadas permaneçam sempre livres. Lembramos que é proibido fumar ou acender qualquer tipo de chama dentro do domo. Os banheiros e bebedouros estão disponíveis no hall de entrada. Ao final do evento, pedimos que levem o lixo até as lixeiras disponíveis no local. Durante a apresentação, recomendamos manter os celulares no modo silencioso, para que todos possam aproveitar o momento. O Instituto Principia agradece a presença de todos e deseja um excelente evento.
O Instituto Principia é um centro de produção e difusão do conhecimento científico e de conexão da ciência com a sociedade. Com atividades científicas desde 1951, tem atualmente 3 programas de atuação relacionados à pesquisa, educação e divulgação científica. No programa de pesquisa, acontecem eventos internacionais sobre temas atuais para diversas áreas da ciência. No programa de educação, a Escola de Talentos oferece oportunidades de desenvolvimento pessoal e acadêmico a jovens que tenham grande interesse e altas habilidades para a ciência, oferecendo uma tutoria científica com pesquisadores renomados. No programa de divulgação científica, existem diversas atividades com ênfase para o público jovem, como o You Science, o cinema científico e publicações em várias redes sociais. Conheça, participe, amplie seus horizontes através da ciência. www.institutoprincipia.org.
And now I want to thank the organizational help from the ICTP-SAIFR, and I invite Nathan Berkowitz to say a few words for us.
Okay, so first of all, thanks. ICTP-SAIFR, I'll just say a few words. We have pamphlets. Some coffee breaks if you want more information. Can you hear? Okay. So we're an organization, as you saw in the video, connected to ICTP in Trieste. We started already 13, 14 years ago. We're also a thematic grant of FAPESP, which means we have associating members not just from our institute, but from, I guess I need to use this. In red, these are the these are the researchers associated with ICTP-SAIFR. So we have from all different areas associated to theoretical physics. Okay, so these are the number of activities. Obviously, we have about 1,000, 1,200 visitors every year coming to our activities. Let me just. Okay, so schools and our main activities are schools and mini courses, which are usually 2-week activities, and this is not working so great. We've had many activities with ICTP in Trieste, including schools on cosmology, schools on particle physics. We also had a 3-week program funded completely by the Simons Foundation. We've done this already 3 years. This is with Perimeter Institute. So this is a school we organize for the top undergraduates from Latin America, and the best students at this school. It's an annual school for 1 week. They can spend 1 year at our center and 1 year in Perimeter Institute in the Psi Master's program. And these are the schools for this year. So, so you can see that they're in all different areas. Usually the first third of the year is on biological physics. Second third is on more high energy theory, high energy physics. And the last part is about quantum systems and artificial intelligence. So of course, this is one of our activities. So these are the schools we have. We also have workshops. So of course, like this activity here, in all different areas. This was an activity funded by Simons Foundation. So we've already had this activity 3 years. It's an activity for 3 weeks where students or where researchers come together to discuss. It's a focused program on something called Bootstrap, related to scattering amplitudes. These are the workshops planned for this year. So of course this is one of the workshops. And we have obviously workshops in all different areas. So if you want to apply to organize activities, I'm going to skip the part about outreach. We have an annual call for activities, which is judged by our scientific council every February. So if you're thinking about organizing activity in 2018, then you have to apply until the end of this year. We also obviously have activities here. In addition to these types of workshops, we're also thinking of having now long-term programs similar to the activities in KITP. We also have, in Principio, we also have research group meetings. So we have them in astrophysics, we have them in biological physics, and we also have them in quantum technologies. Okay, so we also are looking for new professors. Our university has opened 4 new positions at our institute, which is about half an hour away from here by metro in Barra Funda. We're looking in all areas, but especially in biological physics, and we have the advantage of having private funding, which can help to supplement the salary. Okay, so you've already seen a picture of this in the video. Most of the work is, of course, done by these people, and if you want more information, here are the web pages and the media. So I guess I have 5 minutes if people want to ask questions. If not, we'll go to the next part. Any questions or comments or complaints? Not yet. Okay, so I'll go to the next speaker.
Okay. Thank you, Nathan. Now I want to thank the financial support from the Wilhelm and Heraeus Foundation, and I invite Professor Stefan Ujorda to talk some words to us.
So good morning, everyone. And welcome on behalf of the Wilhelm and Heraeus Foundation to this 3rd Brazilian-German Heraeus seminar. It's a particular pleasure to be here for me, and I apologize for all those who do not speak Portuguese, but I really want to say a few words. Então, é uma grande... estou muito feliz de poder estar aqui. Eu passei parte da minha infância no Rio de Janeiro. O que aconteceu agora? Obrigado. Depois comecei a estudar física na Alemanha, quando um dia apareceu a possibilidade de voltar para o Rio para fazer, a ideia era de fazer passar um semestre somente. Acabei entrando no CPPF, no programa de pós-graduação, e eu, como alemão, foi oferecido uma bolsa de mestrado do CNPq na época, que foi uma grande surpresa para mim. Eu aproveitei muito, fiz o mestrado e depois voltei para a Alemanha, então é uma grande felicidade para mim agora poder estar aqui nessa função que eu tenho na fundação, poder devolver algo à comunidade científica brasileira. Obrigado. So I just mentioned that I spent part of my life in my childhood in Rio de Janeiro, and later I came back to the Centro Brasileiro de Pesquisas Físicas, where I made my master's degree. And I'm very happy to be here and in my function now as managing director of the foundation to be able to give something back to the community, to the physics community in Brazil. So, but now let's start saying a few words about our foundation. So in a nutshell, the Wilhelm and Heraeus Foundation is Germany's most important private institution funding physics. We cooperate very strongly with the German Physical Society, and we are best known for organizing and funding a variety of events dedicated to discussion of research results and the training of early career scientists. Our founders were Wilhelm Heinrich Heraeus and Else Heraeus. Wilhelm Heinrich, he was born 1900, he studied physics in Bonn, Munich and Göttingen, and then he moved to the University of Frankfurt, where he completed his PhD in physics in 1923. In his CV, he writes that his advisors were Herr Geheimrat Wachsmuth and Herr Professor Gerlach. So this is, of course, Walter Gerlach, who today is best known for the Stern-Gerlach experiment, which was performed just the year before 1922 in Frankfurt. So these were the exciting years where quantum mechanics was developed, but Wilhelm Heinrich decided to leave academia, and he entered a company which his grandfather had founded in 1861, a company which still exists today. And he spent his whole professional career as manager and entrepreneur in the company. As he and his wife had no kids, but they were very wealthy, and therefore in the 1960s they decided to establish the foundation. After they passed away, all their company shares were transferred into the property of the foundation, and today it's the dividend of these shares which constitutes our regular income. So if the company makes money, they pay a dividend to us. It's good for us, it's good for you, because you can support events like this one here. So the money comes from the company. You see here some key figures about it. It's one of the top 10 family-owned companies in Germany, which includes business in different sectors. The portfolio comprises noble metals and all kind of associated materials and technologies, but Heraeus also delivered several tons of ultra-pure niobium for the superconducting accelerating cavities at the Large Hadron Collider, for example. Portfolio also comprises all kind of quartz glass components. There's even a product manufactured by Heraeus on the moon. This picture shows the lunar laser ranging experiment, which was deployed by Apollo 11 crew. And it mainly consists of triple prisms made from quartz glass, and they were manufactured by Heraeus. And a more recent example, this picture shows two mirrors of gravitational wave detector LIGO. The blanks of these mirrors were also manufactured by Heraeus. So the purpose of the foundation is to support of research and education in science with an emphasis on physics by different activities. We fund school activities, teacher training courses. We organize and fund meetings like this one, of course. I already mentioned that we cooperate with the German Physical Society, and there are many other special projects and prizes, etc. I'm not going to mention in detail. So just to give you a glimpse on what we do in terms of education, we do support different school labs. On the left-hand side, you see a school lab dedicated to spectroscopy and environmental physics at a high school in Germany, or physics camps where high school students can pass a week or a couple of weeks in a lab and learning more about, for example, optics and laser physics. Last year was the International Year of Quantum Science and Technologies. There are also many activities. We funded many activities related to this. Just another example, this little circuit board here on the left side. You see two crossed wires, golden wires, and together with an oscilloscope, with this board, you can see the quantization of conductance, even at school. It's a bit tricky, but you can do it. We also do support different student contests and prizes in the International Young Physicists Tournament. It's a very prominent one, and I know that Brazil has participated during the last years. Here it's called a Copa do Mundo de Física, and last year they went home with a silver medal from the competition in Sweden. Beamline for Schools is another competition where high school students from all over the world can propose certain experiments at CERN. Not at the Large Hadron Collider, obviously, but at a little accelerator, and they can do some own research projects there. Then the other main activity is scientific meetings. So we have a long tradition of organizing the so-called Heraeus seminars. These are 60 to 80 participant workshops, typically 2.5 to 4.5 days, where seniors and early career researchers from all over the world meet and discuss cutting-edge research. The foundation covers the local costs for all the participants and partial travel costs for organizers and speakers. And there are some travel funds available for younger participants from the global south. If you look at our website, you will find all the upcoming seminars. The preferred venue for these events is the Physikzentrum in Bad Honnef. It's a very nice conference center close to Bonn, the former capital of Germany. Here you see a photograph which has a very nice infrastructure. And then there are the binational Heraeus seminars. So this is a Brazilian-German seminar. Here the idea is to, in particular, initiate new or foster existing collaborations between research groups in Germany and the partner country. So these are always joint proposals from physicists from both countries. The venue can be in Germany or the partner country, and we initiated this originally with European partner countries, but extended in meanwhile, and so this is the third Brazilian-German one. We had one with Argentina last year, South Africa, and other countries. Again, here are upcoming seminars, and in addition, we do support many different other types of events like physics schools, summer schools, workshops, symposia, and so on. The preferred venue I mentioned is the Physikzentrum Bad Honnef, but we have also cooperation agreements meanwhile with the, for example, the École de Physique in Les Ouches de Lorentz Center, or also the ICTP in Trieste. So we are running around 2 or 3 events in Trieste every year, as Nathan already mentioned, of course, the strong link between the ICTP-SAIFR and the ICTP in Trieste. And some of the Brazilian-German events we organized or financed during the last years also took place at the International Institute of Physics in Natal in northern Brazil. I also want to briefly mention that we also support the Falling Wall Science Summit. I don't know if some of you have heard about it. It's a international science summit inspired by the fall of the Berlin Wall on 9th of November 1989. So every year around these dates, there is a big science summit in Berlin, and there is a very interesting format called the Falling Walls Lab, where emerging talents from all over the world can pitch their work and present which walls they are going to break down with their own work. So if you are interested in organizing a seminar or a national seminar, first of all, have an idea, find co-organizers. So we always require that there is at least a co-organizer from Germany, like Axel, and there should be certain involvement of the community in Germany. We have biannual board meetings in April and September where our boards decide on applications, and the guidelines can be found on our website. That's all I wanted to say. I will be here around the next day, so please feel free to ask me any questions regarding our program. And at the end, I just want to emphasize, I know that money is important to run such an event, but with money alone you couldn't do anything. So therefore, on behalf of the foundation, many thanks to you, Axel, to Arnaldo, and to Nilsson, and of course also to Nathan and your people here, your staff, who did lots of administrative support and organizational work. So I hope that you enjoy your stay here as much as possible. I'm looking forward to the seminar, and thank you for your attention.
Thank you, Stefan. Now I want to tell you about this workshop, the seminar, sorry. We have challenges on low-dimensional quantum gases. The challenges are also in enhanced and quantum thermal fluctuations. It's about systems in 1D and 2D. We have several topics among them. We have quantum Hall effect. We have simulations of anyons in 1 dimension. We have photon BEC. We have quantum gases in microcavities. And taking the line of quantum gases in microcavities, I invite Smitha Vishveshwara from Urbana, USA, who will talk us about the shell-shaped BECs. You have 40 minutes and five minutes questions. Okay, that's okay?
Yeah. Good morning, everybody. It's an absolute delight to be here, and I've really been looking forward to this, and warm thanks to all the organizers for this invite and putting together this beautiful seminar here. So as we start the seminar this morning, I want to tell you about a journey that we've been taking for almost 20 years now. And it's just the morning, so on a celebratory note, it'll just be a sweeping view of the many things we're doing concerning these beautiful shell-shaped Bose-Einstein condensates. And so just sit back and relax. I'll be here till at least through Thursday, and so we'll have an opportunity to talk about all this in much more detail. Okay, so to tell you where we all started, like I said, I am based in the University of Illinois at Urbana-Champaign, and I've been there almost for a quarter century now. I went there in 2002 as a postdoc, and then I remained there as faculty. So some of this began right at the early stages, and now finally, it's since the past 10 years, it's gone to new heights, and I mean literally new heights, because it's aboard the International Space Station with some of our collaborators. So what I'd like to tell you is, and in particular, it's I do theory, and these are wonderful experiments done about on the Cold Atomic Lab on the International Space Station by, I have to have two things in hand, I realize. Okay, that's been done aboard the International Space Station by the group of Nathan Lundblad, and we are his theory collaborators, and also you'll hear more about the status of where that is right now by the next speaker. So I believe Nathan was here 3 years ago, and he told you a little bit about what's happening here. Not a little bit, a lot that was happening, and I will tell you where we're at right now. But really what I would like to tell you about is the journey that took me from 2002, me and my collaborators, my group members, my students, all the way up to how did we end up on the International Space Station? Okay, but there's actually another journey here, and that's to do with here, I mean literally here, and that's coming to Brazil. It's my first time actually coming to Brazil, and in fact South America at all, which is why I'm again so excited to be here with all of you. And I'd heard so much about the WEH series and ICTP and SAIFR, so finally it's really been a dream to be part of this. I see the wonderful physics that you all do, so it's really wonderful to be part of it. I will say there's one more reason that goes back 20 years. When I started as faculty in Urbana-Champaign, one of the most exciting things I used to do was this, capoeira. so it's been a while since I did it, but it's really part of my blood. If there are any locals who know where to go, please do tell me, I want to go. But so this is why it's just such a delight to be here. Okay, so what will we talk about today? This is more or less the program. Like I said, I will really breeze you through many different parts of the journey, and any of these that you want to know about in detail, I'm happy to talk about. Also, I want to talk to many of you about these things because they overlap with your expertise as well. Okay, so in this story today, I'll tell you about where you might find these shell-shaped structures. You'll see that they exist in quite a few different contexts, and it's really quite exciting. Now, once one of the systems that we started working on was really, you have to learn how to use it's like tick, tick, tick. Okay, one of the systems where we started looking at is coexistent phases of superfluid and Mott insulator with some beautiful experiments on optical lattices. And so I'll tell you a little bit more about where that came about. And so then we will see many of these features. How do you even initialize such a system? What is the collective excitation? What kinds of things can you actually measure? So these are the things that we'll look at. And then I will tell you how we started theoretically dreaming about a few things. For example, if you have something just suspended in free space, how might that evolve? How, if you just do time of flight, what kinds of things do you see? What about vortices and the like? So we just started thinking about that theoretically, and so what I will tell you is about how that actually got us connected to Nathan's group and how that has led to really a beautiful, exciting new part of the journey that has gone up to space. Okay, so this is this is the outline for what I'll talk about. Before I do that, while most of this I do want it to be celebratory, just to open the seminar, there is one solemn moment that I would like to take, and it's because 2 weeks, just a little over 2 weeks ago, I lost my mentor, and he's actually, we as a community lost somebody in the field, namely Tony Leggett. He, Nobel laureate, somebody who really set the stage for a lot of the superfluidity and superconductors that we know about today. He was my postdoctoral mentor when I came to Urbana-Champaign, and ever since he remained a very dear mentor, friend, colleague. And I think one of the things that really highlights his way of thinking is just this curiosity. He was always ready to explore some of the deepest things with a purity of purpose, and he would always listen to everybody. So he started by telling this little girl, he started telling this little girl about superconductors and showing her levitation, but then she started asking him, can you tell me how the moon was formed? And he was sitting there perplexed. So you see this beautiful moment where he's actually learning from the child and thinking with her. So I just want to pay tribute to him. It'll be his birthday this Thursday, and he passed 2 weeks ago. Okay, now for our story. So as I told you, if you look at the outline, the first question is, where do we find these kind of shell-shaped condensates, these shell-shaped superfluids? And the answer is, it's actually hidden in some of the most marvelous of spaces. And so, for example, we already talked about space, and I literally mean space. And if you look at deep space, for example, these very compact stellar objects, neutron stars, the remnants of dead stars, it's got a very beautiful structure inside, and you can see that under tremendous gravity and pressure across the surface from the center all the way up to the outer radius of the neutron star, there can be, the density changes so dramatically across this that you see all kinds of different phases of matter. And so one of the things that you can expect is actually a shell-shaped superfluid region. There's also shell-shaped superconducting regions. So that's very rich, fertile ground. And some of the superfluidity is actually needed to explain things that you see, such as pulsars. These are rotating neutron stars. And you sometimes see a glitch in the rate. They're beautiful timekeepers. And some of the theories that explain this kind of glitch really target that superconducting region. So that's that's a beautiful system. And of course, a lot of it is speculation because we can't really look inside the neutron star. But now with a lot of the LIGO and just the gravitational wave detection and multi-messenger astrophysics, it's becoming more and more palpable to probe these kinds of structures. Another back here on Earth, and at the lowest, the extremely high temperatures there, it's quite a contrast, here, and nothing like can be attained on Earth. And here, of course, as we all know, the coldest states of matter in the universe do exist right here on Earth, thanks to the amazing experimental capability, some of which you all have been actively involved in. So another place where you can find it is in ultra-cold gases. And for example, if you have mixtures of two different species, then fermions and bosons, for example, it's possible to form these kinds of shells. Okay, now another place is optical lattices, where again you can just have bosons loaded up in an optical lattice, and then under certain conditions, it's possible to have coexistent states of matter. So you can have superfluids and Mott insulators coexisting, and when you look at the equilibrium structure that's taken, it is in the form of these kinds of shells. And then finally, there's free space. Is it possible? Well, it is possible with a caveat that we're going to see later in this presentation. And so you could just have these condensates suspended in free space under the right conditions. Okay, all right. So what I'm going to focus on is these two structures, these two systems rather, and these two, for now, we'll let them be, but if anybody is interested, especially this one, it's something that I have a little more knowledge about, something that I'm extremely excited in exploring as an interface between cold atomic physics, cold though at very, very high temperatures. Ask me what cold is later for very high temperatures, and the interface between ultra-cold atomic physics and astrophysics, okay? Okay, so let's go to these optical lattice systems. And as many of you know, roughly speaking, when you have, in the lab, when you have these cold atomic gas setups, it's possible to have interfering laser beams. And so in that sense, you form an optical lattice. And now, so then what you have a kind of, you have a Bose-Hubbard kind of system here. And so when you have hopping on a lattice, roughly speaking, you have some kinetic energy, you have some interaction energy, and then you also have this kind of confining potential. So now if you say, what kind of phases of matter can I realize? Then the answer is, if you look at the Bose-Hubbard phase diagram, it's possible to have, if the interaction energy, repulsive interaction, is extremely strong compared to the kinetic energy, then the bosons prefer to be just localized on a site, and they can't hop back and forth, so they form a Mott insulator. Depending on the chemical potential, if the chemical potential, for example, if you're looking at the bottom of the trap, it's easier to trap more atoms. And so, for example, you may have a Mott insulating state with, say, 3 of these bosons pinned there, while, for example, if you're at a lower chemical potential, then energetically it's more favorable to have fewer number of particles. So in general, this is the phase diagram that you might expect: Mott insulating phases and superfluid phases. This is just, for example, in a homogeneous system. But now, if you have this trapping potential, then these particles here prefer to, these regions here prefer to trap more particles, and the ones outside prefer to trap less. And so what you can really have is a system, let's turn off the kinetic energy, for example, with concentric rings of Mott, or concentric spheres of Mott insulating material here. Okay, so this is the structure that you might have when there's no kinetic energy. And now this was something, and like I told you, Brian DeMarco, my colleague, he was beginning up these experiments back in 2002, and this is when I really got interested in the system, and he really walked me and my collaborator, Courtney Lannert. We just got out of graduate school from UC Santa Barbara. Both of us studied with Matthew Fisher, and so when I started up in Urbana, Brian said, oh, look, there's this really exciting system that I want to build. And so we got very interested in that. And so from the early days, you can see, for example, this is absolutely realizable. Of course, it's gone really much, much, much further now. And through spectroscopy and the like, for example, it can be imaged quite beautifully. So you really see these concentric Mott insulating layers. Okay, so this is in the limit that there's no hopping between these. Now, the moment you have hopping between sites, you can see that you're actually going, the regions where you go from one phase to the other, they're particularly fragile. They're particularly conducive to having number fluctuation. So those are the regions in which you might expect a condensate to form. And so now turn on a little bit of hopping, for example, and so what you really have as you go through that optical lattice system, and let's say you go from the inside deep within to the outside, you can see that between these Mott insulating layers, there's this region where there's a lot of strong fluctuation, and then as long as there's enough hopping, those regions stabilize into these superfluid condensate shells, which you can later which you can show actually has superfluid order. This thing's called the wedding cake structure. Let me go back. This thing's called the wedding cake structure because if you look at the density, the Mott insulator is incompressible, and so you have these regions where the density is flat, then it goes like this, like this, like this, and depending on how elaborate and large your system is, you can have a more elaborate wedding cake, okay? So, all right, so this is again something that's measurable. And so what we did as theorists was to say, let's focus in that, well, we did a couple of things. We showed how through spectroscopy you can actually image these different phases, and it was quite consistent with what was seen in experiment. And then the next thing we said is, let's try to explore this superfluid region. I won't go into the details. I will give you more of a taste of what we did. And this is where the low-dimensional gas aspect comes in. And so what we did was we focused on the region just between these two layers. And for those of you that are interested in the theory, we said, okay, how do we actually model this? So there's a kind of cute representation, a pseudospin representation, where you can say if you're in some Mott phase 3, let's say, that would be the spin pointing up, and then if you're in the other Mott phase, let's say 2, that would be spin pointing down. So there's a very lovely pseudospin description, and again, you have the Bose-Hubbard system, and then if you focus just between these two Mott layers, then you can actually design it through the pseudospin formulation. Okay. So so this is the pseudospin description. If it's pointing up, you don't have any superfluid order. Sorry, I should say condensate order. If you're pointing down, you don't have it either. These are the two Mott states. But anywhere in between, you do have condensate order, and you can see that it's a condensed phase because this spin can point in any direction, but there is net ordering that takes place. There's spontaneous symmetry breaking, U1 symmetry breaking, and that represents the superfluid. So this is a nice pseudospin description of the condensate that you have in these shell-shaped regions. Once we had that description, we said, oh, it opened up a kind of whole world of the kinds of things that these superfluids could do. So we could look at equilibrium properties, we could look at things like collective modes, and so that was one of the first things we looked at. So what does the collective mode structure look like? As you might imagine, and actually this in itself is interesting, and some of you here have studied shell-shaped superfluids in other kinds of systems, or more generally, you could be studying any fluid in some kind of topologically non-trivial geometry where you might have something hollow inside and you might have a filling on the outside, there are some significant traits that are common to any of these structures. So in particular, when you look at this, never mind the details, but if you just look, this is a structure that we're interested in. You have the Mott insulator at the center, let's say, and another one outside, but sandwiched between that is the superfluid layer. And so when you look at when you look at what the collective mode structure looks like, if you have spherical symmetry like we assumed, then you know that you kind of have these collective modes like you would have with a regular superfluid or regular condensate, I should say, in a harmonic trap. But in addition, the fact that you have this, let me just call it hollow region, as far as the superfluid is concerned, gives you a completely different mode kind of structure. So that's something to keep in mind. And more generally, if you have any kind of strange, unique geometry, one of the things that we wanted to ask is, you've probably heard this thing like, can you hear the shape of a drum? So just by looking at the collective nodes is a good place. Please tell me somewhere where I can listen to drumming. I really want to do that. Yeah. So the thing is, if you listen to the sounds and the collective modes, can you actually recreate the shape of a drum? And so we've been thinking about a similar thing. Can you hear the shape of a condensate? And what that really means is, just by looking at the collective mode structure, imagine you have a blob sitting there, can you tell what the shape of it is just by looking at all the possible collective oscillations? So that's something more general, okay? All right, so this was one aspect that we looked at, but then Courtney and me, our groups started asking, okay, experiment has given us this kind of shell-shaped structure, but we're theorists, we can dream. And what's so wonderful about, I think, ultra-cold atoms is that the dreams of theory and experiment come together in such beautiful ways, and you'll see in a little bit how our other dreams started coming alive. So we said, okay, let's just see what happens if we don't have the Mott insulator at all, and let's just see how what are the features of something that is just suspended in space. So I don't have a figure here, but I've already shown you the figure. So now what we're looking at is we're saying, forget about the Mott insulator, let's just think of something that's suspended in free space. So if you look at such a system like that, then one of the very common ways, as many of you not only know, but actually do in experiment, to look at the condensate is if you have a trapped condensate and then you release the trap, you can look at time of flight. And of course, this was the first experiment, Nobel-winning experiment, that even showed the presence of the condensate. So time of flight is, of course, one of the most common probes that we have. And so then we asked ourselves, if you have something suspended in space, is there any way of looking at signatures of this condensate? Is there something new that comes about because of this hollow? And the answer is, of course, yes, otherwise I wouldn't be talking about it. But, so for example, here, now you just have free space, you have these 3D shells, and, you have these shells in 3 dimensions, and if you were to let it go, there's something very different compared to a filled sphere. So what happens is, let's just say this is the radius, and there's no minus, but anyway, you get the picture, just to depict that it's on both sides. What's really interesting is that there's a group velocity associated with this shell, so you can think of the shell right here, and the outer radius tends to go outside, but the inner radius actually tends to go inside. And so what I really have when I look at this is this kind of structure. Boom. So you see, there's this mass accumulation. And this was actually reminiscent of something else that's been studied, and I think, this is a great place to be talking about. It's called the Bose nova. And so it's kind of like a boson nova, and I believe Arnaldo's also looked at it in the past. And so just to say that this is work that there's still open questions here. We know that this happens, and I would be very interested to hear from any of you later as to, is there anything else interesting? Are there correlations that we can see? If there's a condensate versus not, what are signatures? So these are things that are still open and ready to explore if anybody wants to look at it further. Okay, so this was 2007, so it was quite a while back. Oh, by the way, right at the beginning, there is a review article that we put out just this year. So if you're interested, and another thing that I wanted to mention, I'll show you all the people that I've been collaborating with. In recent years, my former student, Brendan Rhino, he's been doing a chunk, like a good fraction of the recent theoretical work. So if you look under his name and mine, and you'll see there's a review article, a lot of this is there as well. Okay, so this was 2007, and we'd been dreaming about all these things, but there was a problem. This was purely theoretical. Why? It's purely theoretical because if you try to create these shell-shaped structures, then in the lab, then what happens is that gravity actually pulls it out like this and makes it like a contact lens shape. And so you really cannot have these kinds of structures. Gravity is so strong that it's not possible to realize it more or less anywhere that humanity can access. But this is the second half of my story, okay? So I think it was about 10 years ago that Nathan Lundblad from Bates College, he called up Courtney and myself and said, "Are you interested in your shell-shaped structures?" We said, "Yes, we're interested," but we didn't think any experimentalist would be because of Earth's gravity. And so he said, "I know, this is why I want to take it to space." Okay. We were so excited. So this was when there was the project to start up the Cold Atomic Lab aboard the International Space Station, and that was to carry, and it does carry, 5 different experiments where microwave gravity is actually, microgravity is needed to probe the science at hand. So Nathan's was one of the 5 experiments. You'll hear more in the next talk about the current status. We've been collaborators for over 10 years now. It was tremendously exciting, and just to show you some of the excitement. So this was in about, I think it was, so first off, that's the home of the Cold Atomic Lab. It's the International Space Station. It's very sad that they may shut it down in, I don't know, 2030. I hope not. I hope something will save it. Anyway, so that's the home. And I visited the Jet Propulsion Lab in California, where a lot of these things were based. And it was in 2020, and it was also really exciting because that's when they were getting the Mars rover also prepared. So you can see these people who look like they're in spacesuits, but they're not. It's just a very sanitized thing where they can't spread germs, but they are preparing to send this thing to space, to Mars. Alongside that, they had just done an upgrade. So the way it works, and it's really great because we get to, hear about what the astronauts had done. When I went to JPL, our Cal means the Cold Atomic Lab, our Cal people were telling us about the physics, and all of a sudden they said, excuse me, just wait a minute, we have to stop. And it's because it was the daily update coming from the astronauts, and it was so wonderful. They were talking in English, Japanese, Russian, or so many different languages, and up there it really is an international, peaceful place to be. So we did hear that, and they just sent an upgrade to the hardware, and they'd sent astronaut Christina Koch, and you can see her putting the Cold Atomic Lab upgrade in as she's floating around as a free spirit doing that. And another very exciting thing is that now she's actually set to go on the lunar mission that's going to go around the moon. I don't know when it's going to happen. There's a new launch for Cal that's going to happen. And again, that's very exciting because they keep telling us we don't know exactly when the launch will happen because we have to wait till the lunar mission gets launched, and every time there's something new that's happening. But I think in the next week or two, we will have the launch for the next upgrade. I unfortunately won't get to go, but my student will get to go and actually see the launch. Okay, this is the exciting kind of environment in which the physics goes on. And so, the first set of experiments from Nathan was done in around this time or a little bit later, and this doesn't actually, so his whole purpose was to realize the shells, and in the next 10 minutes that I have, I will, a little over 10 minutes, anyway, 12 minutes that I have, I will just give you a sweeping view of the kinds of things that Nathan has been doing and that we've been studying. Okay, so bubbles in space. This is the chip. Probably you'll hear more from the next talk on the actual design. This is the atomic chip on which it exists. And again, one of my former students, Carmela Padovic, with whom we worked on quite a bit. Now they've joined New Scientist now, so not scientific, New Scientist as a writer, and so they'd actually covered the beautiful physics here. If you're interested, you can take a look. And essentially, the way they create it is through something called a bubble trap, and this is the exact form of the bubble trap. It can be done quite efficiently. It was proposed by Zobe and Garwe, specifically geared towards realizing this in cold atomic settings. And so there are two tuning parameters, and they can take you from a filled sphere to a hollow sphere. So just going through the entire 3D to 2D crossover from the filled sphere to the hollow shell limit. Okay, so once we have that, and also two of the other organizers here, and along with the group of Vanderlei Barniato, they've looked at, I love the work that you all have been doing on BCC's curvature and 2D limit, and I'd really love to see if some of the ideas that you've been looking at can actually be applied here. That's an angle that we have yet to take, so that's another open question here. Okay, so now, given that, what are the kinds of things we can look at? So first off, it's very easy to look at equilibrium properties. So the starting point is just, I forgot to mention that it's the Gross-Pitevsky, the standard Gross-Pitevsky equation applied to these kinds of potential traps. And then, depending on what we want to look at, we have many different techniques. They could just be looking at Bogoliubov type excitations or Thomas Fermi. Those of you that work on these kinds of things, we use quite a range of techniques to study, depending on what quantity it is, different techniques. So for example, this shows you what gravity does for standard typical numbers. This is zero gravity, and you can already see with just 0.007 of Earth's gravity, it's already completely distorted, which tells you why you really need to be doing this under microgravity conditions. Okay, once Nathan said this is going to really happen, we got really excited and renewed our studies with Verve. And so we looked at a range of things, equilibrium properties and the like. We started studying the collective modes a little more deeply. We started looking at vortices, thermodynamics. So there's a lot of different things that one can do. It's really rich, fertile ground to be studying very beautiful physics. And there's still a lot of work to be done. So one of the things, for example, is you can just look at the collective mode structure. This is a standard hydrodynamics, but applied to this kind of unique kind of geometry. And actually, what we found that's quite nice is that this is the collective mode structure. So I told you the radial modes and the angular modes, but as a function of hollowing out. And you notice that there's this sort of dip. This is in the radial modes. And it was very curious that there was a telltale signature for when the system became hollow. We have some reasons as to why this happens, but this seems to be quite ubiquitous, that when a system undergoes a transition, at least in spherically symmetric cases, the moment the hollowing out happens, somehow all the collective modes seem to converge, and there's a telltale dip. This has actually been seen in the Bose-Fermi mixtures, and so we've been quite excited about that. And then, for example, if you look at the angular modes, you'll actually see that there's this nice kind of restructuring where the moment you have an inner surface, you can have modes on the inside as well as the outside, and these can couple to each other. And so there's some really new physics coming in when you have an inner sort of surface to play with, and that's something that we see in the collective mode structure. This is just one example of the kinds of things, and this is something that we want to look at ultimately in the next generation of experiments on the space station, but in the meanwhile, on Earth as well with Bose and Fermi mixtures, these kinds of things are being seen now. Okay. Then vortices, that's something also that many of you are experts on here. And now you can ask, is the nature of the vortex any different if the system is hollowed out? Or in general, what's the nature of vortices on a spherical surface? And so you can see actually that the flow is such that if you have, and this is true of even hurricanes and things on Earth, this is just mathematical constraints on flow. So if you have, for example, a vortex going around here, and then you go, so somewhere in the northern hemisphere, then somewhere in the south, it says there should also be another tornado, but luckily we have things like dissipation and all that for earthly atmospheres. But in a superfluid, you can always show that if there's one thing going around like this, its partner has to be there somewhere on the sphere. And then that's in general for a spherical surface. But then you can go further and say, if it's hollow, is there any way of saying, I'm not going to go through the details. The answer is yes, because energetically, the moment something becomes hollowed out, then it's easier for this vorticity to go through. And so you can actually see that with even just a slight bit of rotation, it becomes easier and easier to thread a vortex through. I will just comment that I told you about the neutron star and that superfluid surface, and I told you about the pulsar glitch. Let me just say that the picture to have in mind as to why that glitch happens, the answer lies in not one, but a whole tangle of vortices. These are quantized vortices. They carry quantized angular momentum, a tangle of vortices that take place, and then the glitch apparently comes about when there's a sort of massive reconfiguration of these vortices. They snap these vortex lines. So this kind of physics is also applicable to the neutron star setting. And then finally, one of the things that we're doing in detail is we're looking at the thermodynamics, because Nathan's group, they actually go from the filled sphere to the hollowed sphere. And so now it's a kind of expansion that takes place. And so now the question is, if you start off with a condensate, what are the largest structures? And okay, so I'm good. So one thing that's really unique is that these are some of the biggest ultra-cold gases that can be created. I have only 3 minutes, and I have a couple of other things I want to say, so I'm not going to go through the details. You'll hear more about it in the next talk. I will tell you that the entire condensate hasn't actually remained, and there are reasons for it. There's loss of adiabaticity and the like. At the largest structures, that hasn't remained. Why does this look asymmetric? That's because of the atomic chip that I told you about, and you'll hear more about that, I think, in the next talk. All right, so that kind of brings me to the end of my story. It's all been really exciting, and as you heard, last year was the International Year of Quantum Science and Technology. I'm on that IYQ UNESCO-related steering committee, so we get to do a lot of wonderful, wonderful, exciting things. I'm also part of APS, the American Physical Society, doing a lot there. So one of the things we did was Quantum Fest. If any of you went to the APS Global Summit last year, there was a public event, and so, for example, here we actually, it was so wonderful because our JPL NASA collaborators, they had kids come onto stage, among many other things. We also had a circus, real circus, and I have more on that if you want. And these kids, it was great because they pressed some button that went to JPL, that went up to the International Space Station, and in real time, these kids initiated the creation of Bose-Einstein condensates up there in space in real time. That was very exciting, and also these children got to have those condensates named after them. So there's a lot of fun to be had, and let me just conclude. There's many, many different directions that we can go, just looking at realistic thermometry and the like, non-equilibrium, Kibble-Zurich physics. We're also looking at the parallels with expanding universes. Sorry, there's only one that we know of, the universe, one universe, but in the lab we can have many of them. So there's a lot to explore here, and hopefully I've given you a taste of some of the things. And so with that, I just want to thank all my collaborators, Courtney, Nathan, David, he's the JPL connection, many, many other collaborators. These are my former group members that contributed quite a bit, and of course, NASA, NSF, and ICTP-SAIFR and WEH, and I want to really, really thank you all for being here and listening to me. Thank you.
Thank you, Smitha. So any questions?
Thank you very much for the nice talk. A very naive question: to what extent can you do some of these experiments, perhaps only preliminary and perhaps not as well as it could be done later on the space station, with levitated Bose-Einstein condensates?
Oh, sorry, I should say that these are hovering in space. I should have told you that. There are these traps that actually keep them suspended in space. So the entire cold atomic lab really does realize these levitating things. So sorry, I should have specified. Okay, the structures that you see are levitating in space. Yeah.
Well, thank you for the nice presentation. I have a question. It's related to the. You didn't elaborate anything about vortices, but when we do vortices in 2D, even in 2D, but in a flat, we see the vortices being generated at the edge, and then they migrate in.
Yes.
Now, when I have a bubble, I have no edges. So my question is, how you, in what your calculations and things you're doing, where the vortices generate? It must be a little different from the flat.
Yeah. This is a great question. So, and also there are two comments, by the way. One is, so if you're rotating it, what tends to happen is, first off, as you all know, with the vortex and the anti-vortex, they tend to annihilate each other. So one of the things that you have to do is, as you rotate it, you find that you can, if you were to have a formation of the vortex-anti-vortex pair, initially they're trying to annihilate each other, but then the force is keeping them apart. So it turns out that there's always some kind of angle at which it happens, and then there's a critical rotation where it finally goes. That's just one vortex line. But then if you have more, the dynamics becomes much more complex and different from the pancake case. Also, things that you've looked at, the curved manifold, I don't know yet what the effects are for this kind of generation, but the curved manifold also has quite a strong effect. So, great question.
Another fast question.
Yeah.
How temperature changed some of the things you showed to us on the transition of multi-isolator and things?
Okay, thank you. Actually, I may as well talk about what it does with these bubbles in space, because I didn't get to cover that. Temperature is actually quite bad, and it's in the following way. Suppose you start at low enough temperature to have a condensate. One of the problems is, as you grow bigger and bigger, you become more dilute. So TC also starts plummeting down. And temperature ends up being quite bad because there's adiabatic expansion, so the system cools. However, it cannot keep up with the decline in TC. So one of the things that happens is that it goes into a normal phase. And there's very, very interesting dynamics there, where non-equilibrium dynamics, where it crosses into a normal phase. It kills the condensate order, and that's where you can have some you fall out of adiabaticity, and you have some very highly non-equilibrium behavior. So that's a really good question.
Any questions? I think I go the other route.
Really nice presentation. So just to add to his question, so my thing is that you had mentioned that vortices, they form, what I believe is you mentioned there is self-interference patterns, right? So I believe that it could be due to those interference patterns where these could evolve into like soliton structures. In 3D, it will be like ring solitons.
Right.
And these would break.
Yes.
Which is known as a snake instability.
Yeah.
Which is observed, yeah.
Exactly.
So I think that could be, is that what's happening here, which you're mentioning?
Actually, so no, this is also a really good point, and there's a lot to be studied, by the way. So I will say that this thing is more sort of the force that wants the vortices to come together. Like if you have a smoke ring, right? Like you really have to give some sort of Lorentz force and make it grow bigger. Yeah. So in some sense, the rotation does that. But you raised a really good point about the whole, the snaking instability and things. We have not studied that in depth, but we've speculated that especially as you go from sort of a 3D structure where that sort of the tension, the line tension of the vortex plays a big role. And then as you hollow it out, does it get less and less? At the same time, we know that in 2D things get more fragile, so there will be an interplay. We have not studied it, but we've thought about it, so maybe something to be discussed.
Okay,
Yeah.
thank you.
Okay, I think we are on time. Let's thank Smitha for the nice presentation.
Thank you.